Welcome back, everybody. This is AP Chemistry, Unit 13, and we're taking a look actually at I know the screen says section 2, but we're actually in Section 3, and I wanted to start with this screen because it does summarize the rate laws that we've been studying for kinetics. So the rate laws, there's two different types. In the first section, we looked at differential rate law. That was taking a look at a rate of reaction that depends on concentrations, and then the integrated rate law takes a look at the concentrations as a function of time. So function of concentration versus time is going to be the big part of it, because we typically consider reactions only under conditions when the reverse reaction is unimportant. Our rate laws will be involved only the concentrations of the reactions. Because the differential and integrated rate laws for a given reaction are related in a well-defined way, the experimental determination of either of the rate laws is good enough, okay? So experimental convenience usually dictates which type of rate law is being determined experimentally. So it's just whatever we end up working with, and we use that data to figure out what's going on. Now, this is why I'm showing it, is because using these rate laws, knowing which the rate law for a reaction is important, because we can usually infer the individual steps involved in the reaction from the specific form of the rate law. So this last section is all about the steps, okay? So we're going to be modeling the chemical kinetics as we go. And so we need to understand that the more concentrated the reactants, the faster the reaction. The higher the temperature that speeds up the action of those things, the faster the reaction. And that actually is going to go right into the collision theory. Okay, molecules are going to move towards each other. They hit with the proper orientation. They must hit with sufficient energy, and they're going to separate after the reaction occurs. And so the collision theory explains all of this. And so what we're seeing with the graph in an endothermic reaction is we're modeling this out, and I see that on endothermic, we got to add a certain amount of energy, and then all of a sudden the reaction will take off. Exothermic, we get a certain amount of energy in there, but all of a sudden we drop down below, and we see that we're actually emitting some of that energy. Notice here that we see we see a positive heat here, and so energy needs to constantly be added to it. We always have to have a activation energy that goes with it. Sometimes you have a catalyst, and that's going to lower that activation energy, but it's always look at the end to see where that energy ends up, okay? So that's just modeling it out a little bit. Now let's take a look at that activation energy to start with this. We've got two different ways that we could look at it. We don't typically use this way. Okay, this is kind of a complex way of doing it. We don't typically use this way. We tend to use this equation. Okay, this is the one that we primarily use. We have the natural log of your Ks, and that will be your activation energy over the R value times your 1 over temperature 1 and 1 over temperature 2. And so we can just plug values in and calculate that activation energy just doing those. And I'm not going to really walk you through that type of problem. We can see that in the solution. We saw those values that were given. And so we can substitute the values in and just plug them in. And we see that you plug in your temperatures, you plug in your activation energies, you got your natural log, your concentrate, or your Ks. And so then we see that we end up with a value of an activation energy of 1.4 times 10 to the fifth joules per mole. Okay, so just a substitution thing, just know your equation. Okay, now for a reaction to be plausible, okay, we got to see that the steps must give the overall reaction, and that the rate law derived must agree with the observed mechanism from the experimental data. And so what we see here is, in this particular example, we see a fast step and we see a slow step. And the slow in all of this is what's going to determine my actual rate. This is my rate determining step. Whatever you see slow, that's my rate step. And remember that my oxygen must be to the zero order, the zeroth order. Okay, and so we got to know our orders in there, but my oxygen needs to be to the zero order in there. Okay, and so when we get the overall reaction, we're going to be seeing that we basically just have to cancel out things. Okay, so when we do that, I see the overall reaction ends up being NO plus O2 yields 2NO2. Okay, to do this, we have to actually introduce our intermediate step. Okay, so the reaction is going to be this, and so what I need to do is I need to see how things are going to be canceling out. Okay, and so within this, I see that this guy is my N2O2, and I see that I'm missing on this side. I see where the confusion is. This needs to be a 2NO2, and that's a fast one as well. Okay, so basically what's happening is I see that I get my NO plus my O2 will yield my 2NO2, and we would refer to this one as N2O2 is my intermediate. Okay, N2O2 is produced, but then it's consumed to do the next one. So this is important in identifying different mechanisms. And so when I see that going, I see that my rate, if my oxygen is to the 0th power, I see that my rate then would be K, and then the concentration of NO, and it'd be squared. Okay, so since the steps seem to agree with the experimental data, then we would agree that this would be a plausible type of reaction. Okay, so all we do is basically do some canceling out, see what goes, and see if that would agree that my rate would go with that. So now let's take a look at another one. They're telling me in the problem that I've got a rate of this. Okay, and so I see what's going on with this one, and I see, okay, let's cancel out. All right, so if I look on both sides, this is my equation, and here's the rate for it. So let's see what's going on in this case. It looks like I got one of these is going to be canceling out, and it looks like this is also canceling out. Okay, and so what I end up with in the overall reaction is NO2 is going to produce, oh, sorry, and then I have my carbon monoxide is going to produce my NO plus my CO2. Okay, and so this is my rate determining step. And so I would say if I was going to be analyzing this, I would see that my rate is going to be my K times my NO2 squared. Okay, and so looks like, yes, this would be my rate with that one. Okay, NO2 is right here. All right, so my intermediate would be the nitrogen trioxide, and that's going to be produced and then consumed up. This one is going to be a reactant and then a product at the end, and so that's how we would analyze that particular one. All right, let's take a look at the third example. Okay, a third example here would be now taking a look and seeing if it's a plausible mechanism. Okay, so once again, let's be taking a look. Here's what the equation is, and they're telling me that the rate would be this. Okay, so let's see what happens. And my slow step is my rate determining step. So let's see what happens with this. Now I can produce my nitrogen, and then it'll be consumed. That will produce a single oxygen, and that will be consumed. And so what do I end up with? Well, I have two of my hydrogens here, and I have two of my nitrogen monoxides, and that will produce what appears to be nitrogen gas and two of my waters. Okay, so if I'm just looking at all that, does that seem to match? Yes, that seems to match in this case, at least in terms of the reaction. Now let's take a look at the rate law. Okay, the rate of what we're seeing here is going to be K times my hydrogen over my nitrogen monoxide. Okay, is that the rate of what I'm seeing? Okay, I'm not seeing, because this, and remember this is a liquid, so that's not in there. So this is going to be just 1 over that. So I don't see this to be a match. Okay, this is not going to be a match in this step because this does not match up with my rate laws. Okay, the slow step is my rate determining step. That does not match up with my experimental data. Okay, that's what this is. So this is my product. These are my reactants, but it's 1 over that, so that's why we're multiplying. So I would not say this is a good representation or a plausible mechanism for that particular reaction. Next, we're going to look at this one, and this will be our very last one. We look to our slow step, if you remember. So let's do some canceling along the way. All right, so with this one, I see that my bromine, I'm getting rid of one bromine here, okay, just one of them. And I see that I am going to be using up my bromine here, okay. I see that I've got bromine, and I'm going to get rid of one of the bromine here. And let's see. I've got one bromine still here, and I have a hydrogen. Okay. And that looks to be about it, doesn't it? So I have my bromine here. I have hydrogen here, and I have these here. What is the overall reaction? I have H2 plus Br2. Okay. Let's see here. I got rid of two of these and two of these. I'm going to get one of these left over. Okay. And so then I have, let's see, that's canceled, that's canceled. Good. I'm just double checking everything. And so then I'll end up with two HBRs. Okay. That's my reaction for this one. Now, we're going to take a look at our slow step. What are we getting in our slow step? My slow step is going to be the rate is going to be equal to the K times my Br times my H2. Okay, and so that means my intermediates are going to be my H and my Br. And so the Br then, notice the Br is just kind of floating around in there, but it's kind of unaccounted for. Okay, well, that's why I was a little kind of lost in there. It's like, well, wait a minute. That means that this Br must be a catalyst. Br is a catalyst in this case. It's not really involved in the equation at all. We just kind of take a look at it. It's not part of the reaction. It's introduced and it remains, but it's never been actually accounted for in it. So it's just a part of, not a part of the reaction, but just getting it to go. So it's just analyzing the different mechanisms with that. Look to your slow step to see what's going on. And guess what? This is the end of the section 3. Just taking a look at different mechanisms and taking a look at the different orders with it. You should have enough to go by, and good luck.